In this video, we'll talk about hypothesis testing. I'm going to start with an example from the textbook to give you an idea of what kind of problems hypothesis testing deals with. In this example, we consider a leading laptop battery manufacturer, Fearsome Intensity Batteries. This company created a battery model U500, and the company claims that the battery has an expected runtime of 500 minutes on a single charge. And suppose you are an editor at an IT magazine and you want to evaluate the performance of the battery. You want to know whether the company's claim is the fact or not. So your team got your hands on 45 new batteries and you test them. You find that the average runtime of the 45 batteries is 455 minutes with a sample standard deviation of 32 minutes. What should you say about the company's claim? Well, if you just look at the point estimate, 455, it looks like that is lower than the population, than the claimed population expectation, 500 minutes. But you also found a sizable standard deviation. You also found a sizable variation in the battery runtime. So could this difference between 500 and 455 be due to the sample variation? Could it be, once you take into account the sample variation, is this still evidence against their claim? And this is what hypothesis testing deals with. Now let's translate the story into mathematics. Let X denote the runtime of a random U500 battery. And the expectation of that is mu. Suppose we denote that expectation by mu. Then the company's claim is that mu equals 500. And now you want to evaluate this claim using the data set that you have. In your data set, you have an IID draw of the runtime where n equals 45. And your sample average, that is your point estimate for the population expectation, is 455. And the sample standard deviation is 32. So can you conclude that the company overstated the average runtime from this data set or not? And that's a question that hypothesis testing is designed to answer. But before introducing the hypothesis testing, I want to show you that using the technology that we have learned so far, we can already get some answer to this question. So to answer this question, we could think about answering the following question. What is the probability that the average runtime of 45 batteries is less than or equal to what we observe in our sample? Answering this question is useful, right? So suppose what they claim is true. But the probability that average runtime, suppose what they claim is true, then what we observe is 455. 455 shouldn't be a too extreme event because we have already observed this event. So if this is true, then the probability is reasonable to think that the probability that the average runtime of 45 batteries being less than or equal to 455 shouldn't be too small. if that probability is very, very small, then that's probably evidence that our premise is wrong. That's probably evidence against the company's claim. So we can actually calculate this probability using the techniques that we used in last videos. So what is the probability that xn bar is less than 455 given that mu equals 500? Given that mu equals 500, this probability can be written the probability that xn bar minus mu divided by the standard deviation times square root n less than or equal to square root n 455 minus mu divided by standard deviation given mu equals 500. These two probabilities are equal because the transformation that we made on both sides are strictly increasing transformations, right? The reason that we do this transformation, we demonstrated that in last videos that doing this will help us to calculate this probability. The reason that it helps us is because we know by central limit theorem and continuous mapping theorem that this random variable converges in distribution to standard normal as the sample size goes to infinity, which means that at large sample size, suppose we can treat 45 as a large sample size. At large sample size, the distribution of this random variable is approximated by standard normal. So therefore, we can use standard normal to approximate the distribution of this random variable, and this probability will become standard normal CDF evaluated at this point. And now we can plug in mu equals 500 here. So you get root n for 455 minus 500 divided by 32, which is the sample standard deviation. And that is, and square root n, remember, is square root of 45. So this square root n here, you can write it as square root of 45. So that is phi of minus square root 45 times 45 divided by 32, right? 455 minus 500 is minus 45. So we can do this calculation. I'm going to do it right now on my computer and see what this number is. And that number turns out to be phi of minus 9.4 approximately. Or in other words, is 1 minus phi of 9.4. And that is a very, very small probability. That's less than 0.0001. So that's less than 0.01%. So if the company's claim is credible, then the probability that you observe a average runtime of 455 or less is less than 0.01%. But given that you already observe something, that satisfy this inequality, that probably means that your premises is wrong. Mu is probably not 500. So that's a way that we can evaluate the hypothesis of the claim of the company using the calculation techniques that we have done already using in previous videos. But now that's probably not so satisfactory because this is kind of more heuristic than what we want. So let's now set up the more formal and rigorous hypothesis testing framework. So in the formal hypothesis testing framework, we want to first define hypotheses because we're testing hypotheses. So what are hypotheses? There are two kinds of hypotheses. The null hypothesis, which is denoted capital H sub 0. And the null hypothesis is the hypothesis that we give the benefit of doubt. So in the example, in the battery example, the company claims that their average runtime is 500. We want to give them the benefit of doubt, right? Without, until proven guilty, they are innocent. So until we prove that what they claim is wrong, we believe their claim. And therefore, we set the null hypothesis to be what they claim to be true. So the null hypothesis is the hypothesis that we believe to be true, that we give the benefit of doubt, meaning that we believe to be true without evidence for otherwise. Okay, so typically in hypothesis testing, the null hypothesis will be a simple hypothesis. So what does simple hypothesis mean? A simple hypothesis is a hypothesis that contains only one point. That's a hypothesis that contains only one point. In this example, the point of 500, that is 1 point. So a simple hypothesis is one that restricts the parameter of interest. In this case, it is mu, the parameter to one value. So a simple hypothesis is a simple hypothesis is a hypothesis that restricts the parameter to one value. And so that is the null hypothesis. We typically want it to be a simple hypothesis, and we will get back to why we want this to be a simple hypothesis later on when we talk about constructing the test for the hypothesis. And opposite to the null hypothesis, there is the alternative hypothesis. The alternative hypothesis is the hypothesis that we want to believe when the null hypothesis is proven to be false. So when H naught is false, what do we want to believe? That would be our alternative hypothesis. In hypothesis testing, typically the alternative hypothesis is what we want to prove to be true. And you might encounter two kinds of alternative hypotheses. There are more, but typically there are two kinds, one-sided and two-sided alternative hypotheses. So one-sided hypothesis is an interval on one side of the null value of the parameter, the value that the null hypothesis restrict the parameter to. And the two-sided hypothesis is on two sides. It's a set that contains point on both sides of the null value. So in the battery case, because you want to prove that, because you have doubts about the company's claim and you want to prove that they overstated their battery runtime, if that is what you want to prove, then you might want to consider the one-sided hypothesis, because you want to prove that the battery runtime is not as good as what the company claims. But if you have no bias at all, you had no prior belief about the battery at all, and you have no bias at all, and you just want to know whether their claim is true or not, then you might want to consider the two-sided alternative. If you want to prove that their battery runtime is lower than 500, you consider the one-sided alternative. If you want to prove that their battery runtime is different from 500, could be low or could be high, then you consider the two-sided alternative hypothesis. So these are the definition of the null hypothesis and the alternative hypothesis. Let's now define what is a hypothesis test. A hypothesis test is nothing but a decision rule. It's a decision rule. And this decision rule is binary. You make a binary decision, whether you either you reject the null hypothesis or you do not reject the null hypothesis. That decision rule is a mapping from the data from your random sample into your decision, into your binary decision. So the decision rule is a random decision rule. It depends on the data. It maps the data into a binary decision. Now, to fix ideas, let's consider an example, the example of the battery runtime. In the battery runtime example, the null hypothesis is expected runtime mu equals 500. So that is the company's claim, and we set it as the null hypothesis because that is the hypothesis we want to give the benefit of doubt, and because this is a simple hypothesis. And because we want to prove that the company maybe overstated the runtime of their battery, so we set the alternative to be the one-sided alternative, mu less than 500. And we want to evaluate this hypothesis based on a data set, which is an IID sample from their population of batteries. And the population of batteries has an expected runtime of mu. Now, how do you evaluate this hypothesis? It's clearly natural to base your decision on the point estimate for the expected runtime, because the point estimate is supposed to be a guess for the expected runtime. So it's natural to base your decision on the point estimate, which is the sample average. And it's reasonable to set up your decision rule, which is usually denoted by phi n to be 1 if your xn bar, the estimated runtime to be smaller than some quantity C. Now, this is the usual notation for a hypothesis test. The hypothesis test is a binary decision rule. In mathematics, is a binary random variable, a Bernoulli random variable that takes a value 1 or 0. It takes the value 1. The value 1 indicates that you reject the null hypothesis, and the value 0 indicates that you do not reject the null hypothesis. And in this example of the battery runtime, it is reasonable to reject the null hypothesis when the estimated runtime is too small. So therefore, it is reasonable to use a decision rule that's of this form. But then there is the problem of what should C be? So C is a threshold that is to be determined. I know that when the estimated expected runtime is too low, I should reject the null hypothesis. But how low is too low? And that's determined by the C. And how do you determine the C? Let's do some calculation. How do you determine the C? In order to discuss how we determine the C, the threshold, we want to introduce some concepts of error, of testing error. Because your test is a binary decision, it tells you whether to reject the null or not to reject the null. It could make a wrong decision. You could be making a wrong decision because you do not know whether the null hypothesis is true or not. You only observe a finite sample from the population, so you could be making errors. And there are two types of errors, the type 1 error and the type 2 error. What is the type 1 error? Type 1 error is an error that you make when the null hypothesis is true. Because when the null hypothesis is true, and if you determine not to reject it, then you are not making an error. And only when you reject the null hypothesis, when H naught is true, you are making an error. So when H naught is true, but you reject it, then you are making an error, and that error is called the type 1 error. In contrast, when the null hypothesis is false, but your test doesn't reject it, your test should reject it because it is false, but it doesn't, then your test is making an error, and that kind of error is called the type 2 error. So type 1 error is sometimes called the false rejection, and the type 2 error is sometimes called the false acceptance. When we analyze a test, both type 1 error and type 2 errors are important. We do not want to make these errors, even though they are unavoidable, but we want to minimize the errors in some well-defined sense. And so what is the sense in which we can minimize the errors? Now let's get back to the 2 point of view that we have been discussing. So there is this exposed view and ex ante view for any random experiment. Exposed is after we observe the random sample, after we use the information in our random sample. After we use the information in the random sample, the decision rule is realized. The test is realized to be either 1 or 0. We know what the test does. We know what the decision is. We know what the decision of the test is, but we do not know the true mu. Therefore, we do not know whether the null hypothesis holds or not. So therefore, if an error has been made, then it has been made. If it has not been made, then it has not been made. But we do not know whether an error has been made or not. So exposed, there is nothing we can say about the error because we simply do not know whether we made the error or not. So exposed is not a very useful point of view for evaluating the test or to for talking about how to minimize the errors. This is just like for estimators or confidence intervals. The exposed point of view is just not very useful for evaluating the properties of an estimator or a property of a confidence interval. The same thing here, exposed point of view, is not very useful for discussing the errors of a test. On the other hand, ex ante, before we use the numbers in our random sample, phi n, the test, is still random. It's still a random Bernoulli random variable. If it is a random variable, we can analyze the probability that it equals 1, given some value of the true distribution. Ex ante, we can analyze the probability that it makes an error or not make an error, given some value of the population expectation. And that is the useful point of view to use when we discuss the errors that hypothesis test makes. Now let's go back to the example of the battery runtime. For the battery runtime, so suppose we, so for the battery runtime, the null hypothesis is mu equals 500, and the alternative is that mu is less than 500. And suppose we consider a null hypothesis, suppose we consider a hypothesis test that rejects the null when the observed, when the estimated expected runtime is too low, is too much below 500. So on previous page, I was writing it as 1 xn bar less than some threshold. Now equivalently, we can also write it as rejection if the difference between xn bar minus and 500 is, the difference between them is too large in the direction that xn bar being lower than 500. Of course, so if you write it this way, that threshold and this threshold should be different. But since we haven't determined what this threshold should be, we're just using this as the structure, the general structure of the test. It doesn't matter. This difference doesn't really matter. Okay, so the test is of this form, and this test can make errors. When the null is true, that's when mu equals 500, we can analyze the probability of rejection, which is the probability of type 1 error. The probability of type 1 error is the probability that minus x in bar minus 500 greater than the threshold given mu equals 500. And this probability is the probability of type 1 error. I should write this more clearly. This is type 1. And it is also sometimes called the null rejection rate because this is the rejection rate, rejection probability under the null hypothesis. So that's called null rejection rate. And you can also analyze the probability of type 2 error by fixing the true expectation at some value that's less than 500. For some mu1 that's less than 500, you fix the mu at this value and calculate the probability of rejection. The probability of rejection under a mu that is in the alternative is called the power of the test, and it is 1 minus the probability of making type 2 error. Because the type 2 error is a non-rejection when there should be rejection. So the probability of rejection when there should be rejection is 1 minus probability of type 2 error. So these are type 1 error and type 2 error in the example. And now looking at these two errors, two rejection probabilities, and look at their relationship with the threshold C. As you can see, when you increase the threshold C, both probabilities decrease. So when C increases, prob of type 1 error decreases, right? Because when you increase the C, then it's harder for this inequality to hold and the probability decreases. Increasing the threshold makes rejection less likely, and the probability of false rejection, therefore, is also smaller. So C increases, probability of type 1 error decreases. Similarly, when C increases, this probability also decreases. But that is 1 minus probability of type 2 error. So that means type 2 error, probability of type 2 error increases. So when C increases, when you choose a bigger threshold, you decrease type 1 error, but you increase type 2 error. And reversely, if you decrease C, if you use a smaller threshold, then type 1 error increases and type 2 error decreases. So as you can see, there is a trade-off between these two types of errors. We cannot minimize both at the same time. So how do we balance these two errors? You can think of many reasonable ways to balance the two probabilities of errors, the probability of both the two errors. But there is a convention in hypothesis testing that treat type 1 error and type 2 error in different ways. So what is the convention in hypothesis testing? The convention in hypothesis testing is as follows. By the convention, we're going to need to predetermine a significance level. A significance level is basically a small number between 0 and 1, a small probability number. You predetermine a significance level, say alpha. This alpha typically is a small number, typically below 20%, and typically much below 20%. Typically maybe 1%, 5%, or 10%. But you choose one. You choose a significance level alpha. And then once you determine this significance level, you select your C, the threshold, to be the smallest to still satisfy this inequality. What is this inequality? You are trying to control the null rejection probability or the probability of type 1 error to be below alpha. So that is the probability of type 1 error, or the null rejection probability. So the conventional hypothesis testing really doesn't want false rejection to happen very often. You want to first and foremost make the false rejection probability or probability of type 1 error to be below some small number. And you want the threshold to be the smallest that makes sure that the false rejection probability to be below that small number alpha. Why the smallest? Because bigger C will increase the probability of type 2 error. So you want to control the probability of type 1 error at a level below or equal to alpha, at the same time not to make the probability of type 2 error too big. So that logic determines that C should be selected to be the smallest number that still satisfies this inequality. Typically, although not always, this will require the probability of type 1 error to be equal to alpha. And that's the case whenever the distribution of this random variable is continuous. Whenever the distribution of this is continuous, this requirement will imply the probability of type 1 error equals alpha. And let's see this happen in the example that we are considering. Now consider our example of the battery runtime. In the battery runtime example, we want to make sure that this probability is less than or equal to alpha. We want to choose the C to be the smallest so that this probability is less than or equal to alpha. And I want to also mention that we won't actually be able to exactly or very accurately, 100% accurately, make sure that this inequality happens. The reason that we cannot do that is we typically do not know the distribution of this, even if we assume mu equals 500. That's because we typically do not assume a distribution for our random sample. We do not assume normality, for example. But often we can use asymptotic distribution of this to approximate the actual distribution. So in that case, we should be requiring this inequality to be asymptotically satisfied or approximately satisfied. Asymptotically means approximately in large samples. So let's try to work on this probability and see what it leads us. So this event is the same as the event that root n xn bar minus 500 divided by the sample standard deviation greater than C times square root n divided by sigma n hat, given that the null hypotheses hold, which is mu equals 500. And you see when mu equals 500, this 500 is the true expectation of the data, right? That's the true expectation. So 500 is mu when mu equals 500. In previous videos, we have shown that this random variable is in fact converging in probability to standard normal. We show that using the central limit theorem as well as the continuous mapping theorem. So we show that this converges to standard normal as the sample size goes to infinity. So that means in large samples, let's say n is the large sample, 45, n equals 45 is a large sample. Suppose that is a large sample, this can be well approximated by probability of a normal random variable minus the normal random variable, standard normal, minus standard normal is still standard normal, so we can ignore that minus sign. It's because the standard normal random variable is symmetric. Distribution of a standard normal random variable is symmetric. So that's a standard normal greater than root NC divided by sigma n hat. And that is 1 minus the CDF of standard normal evaluated at root NC sigma n hat. So where phi is the CDF of standard normal. So we want this to be less than or equal to alpha. We are not able to 100% make that happen because we do not know the exact distribution of this even under H0. But we know this is approximately that. So we can make that to be approximately less than or equal to alpha by making this less than or equal to alpha. So what we will do is to make this less than or equal to alpha. And you will see that this implies phi of root NC sigma n hat less than 1 minus alpha. Or in other words, root NC over sigma n hat being greater than or equal to Z alpha, which remember is the Z-score for the standard normal distribution, which is the 1 minus alpha quantile of the standard normal distribution. Or in other words, is the inverse CDF of the standard normal distribution evaluated at alpha, at 1 minus alpha. Or if you want to find the values, the admissible values for C, that will be greater than or equal to sigma n hat divided by root n Z alpha. The smallest possible, the smallest one that satisfies this inequality is this lower bound. See, satisfying this is C equals sigma n hat divided by root n times Z alpha. So that should be the threshold that you use for the test. For the test for the null hypothesis, mu equals 500. So that's how you find the threshold. And this is also the reason that we want the null hypothesis to be a simple one. When the null hypothesis is a simple one like this, it fixes the value of mu. When that is the case, we are able to know exactly what the asymptotic distribution of this random variable is. So we will know a distribution to use to come up with the threshold. If H0 is not a simple hypothesis, then there are many possible distributions of this random variable under the null, and it would be somewhat more complicated when you try to figure out the threshold. So this is why typically we want the null hypothesis to be a simple hypothesis. All right, so this is what we figured out. That's our test for the battery runtime example. So we want to reject the null hypothesis if xn bar is this much more lower than 500, this much lower than 500 or more. Okay, so if xn bar, if the observed average runtime in the sample of a sample of size 45 and standard deviation 32, sigma n hat is if in a sample of size n and standard deviation sigma n hat, we observe an average runtime that is this much or more, less than 500, then we reject the null hypothesis. Otherwise, we do not reject the null hypothesis. So this is what this formula means. Okay, so we reject the null when this inequality holds and do not reject the null otherwise. It is useful, however, to write this rejection rule as the following form, which is equivalent, but it's useful to write in this different form. Right, so from the derivation for the threshold, you already know that this and this inequality, these are equivalent. And so these are two equivalent ways to write the same rejection rule. But considering this expression is useful because because the inequality inside the indicator function separates the random part, which is this, and the non-random part. The random part will be called the test statistic, and the non-random part is called the critical value. So that is the test statistic. It is random. It is a function of the data. And this Z alpha is the critical value. In most of the problems that we encounter, I guess all the problems that we encounter, the critical value will be taken to be something non-random. Although this is not generally true, not in general true for all hypothesis testing problems, but for the ones that we will encounter, the critical value will be non-random. So this formula, this representation of the hypothesis test that we constructed separates the random part from the non-random part. We call the random part the test statistic and the non-random part the critical value. So more formally, what is a test statistic? A test statistic is a statistic. And what is a statistic? A statistic is a function of the data. A statistic whose large values provide evidence against the null hypothesis. So when the value of the test statistic is large, it indicates that the null is probably not true. So that's one requirement for the test statistic. And it's satisfied in this case because this test statistic is large when xn bar is much lower than 500, and xn bar being much lower than 500 is evidence for the alternative hypothesis that the expected runtime is less than 500. So large values of the test statistic should provide evidence for H1 or against H0. And that's the first requirement for the test statistic. The second requirement is that the asymptotic distribution of the test statistic should be known if we assume the null hypothesis is true. So the distribution or asymptotic distribution of the test statistic should be known under the null hypothesis, assuming that the null hypothesis is true. And this requirement is also satisfied in this example because the asymptotic distribution of this is standard normal under H0. Under H0, 500 is the true mean. So this is the sample mean minus the population expectation divided by a standard deviation estimator multiplied by square root n. From previous videos, we know that's asymptotically standard normal. Okay. The reason that we want the distribution of this to be known under the null is that we want to be able to come up with the critical value that satisfies our requirement that the probability of type 1 error should be less than or equal to alpha. And that was exactly how we figured out this critical value on this previous page. We used the asymptotic distribution of this guy under the null hypothesis to figure out the threshold and ultimately this critical value. So that's the formal definition of the test statistic. So what is the formal definition of the critical value? The critical value is the threshold for which the test statistic has to cross in order to reject the null hypothesis. So we know large values of the test statistic is evidence against the null, but how large is large enough in order for us to say that the null should be rejected? And that is determined by the critical value. Critical value is that threshold for the test statistic to cross in order to reject the null hypothesis. So these are the definition of test statistic and critical value. And in particular, in this example, this statistic is called the T statistic. So T statistic is not, I want to say is that you don't always use T statistics. You sometimes use other test statistics. But for the example of the battery runtime, we were testing about the population expectation. Whenever we test about population expectation, it's convenient to use this statistic as a way to generate the test statistic, and that is the t-statistic. Our test statistic is the minus of the t-statistic. So that is the t-statistic. And we use the negative of the t-statistic as our test statistic. And we use a one-sided normal critical value. So that's a one-sided normal critical value as critical value. Whenever we use a negative or absolute value or the t-statistic as the test statistic, and we use a normal critical value as critical value, we are doing a t-test. So, or we're doing a large sample t-test. Large sample t-test meaning that we're using the standard normal critical value instead of a t-critical value. Right? And standard normal is based on large sample distribution of the test statistic. So that test is a large sample t-test. It is a large sample one-sided t-test because our alternative is a one-sided alternative. So this particular test is a large sample one-sided t-test.